Welcome to Opengyan video series. In this video series of videos, we are going to see about one aspect of computer science which is very important and which is a very trending subject. If we see over here in this graph, we see a graph which is in an uptrend, and this has been the case for this scenario or this field for the past more than 10 to 12 years. And yes, we are talking about computer architecture. It's a computer architecture which is the basis of all the programs, all the softwares, all the magic that the computer does. So if we see the trending graph as is the courtesy of the quantitative approach to computer architecture by Jonathan Hennessy, in the last few years from 1978 to 1986, the growth of computer performance has been around 25% per year. But then from 1986 to almost like 2003, the growth has been a whooping or a phenomenal 52% per year. That's the performance improvement that I would say. And then afterwards, from 2006 onwards, it is a modest 22% per year, which is by no means a mean feat. In this 52% per year growth that has been seen, is it all because of Moore's law? Moore's law just says double the number of transistors per chip in 18 months to 24 months, and that's what we see. If that has been the case, then we should be seeing a more than or a sustained growth even over here. And also, if we see the next trend, it says by 2003 we have come or we have hit 3.2 gigahertz in the Intel Pentium 4 Xeon processors, but the Intel Nalem Xeon processor in 2010 has still hit only 3.3 gigahertz. It's just a 1.1% improvement over the years. But if you see in the trend by Moore's law, we have been 15% initially and then a whooping 40% per year. So between the period of 1986 to around 2003, it has always been the Moore's law that has been the contributing factor. Improve the performance, put in more ICs per chip, and you get better performance. But then the chip performance has been little bit flat in the last few decades, in the last decade or so. So 2003 to 2013, we have been seeing only a 1% growth. But we saw a 22% growth in the last decade. How is that so? That's where Amdahl's law comes into picture. Amdahl's law states the percentage of improvement in performance is dependent on the amount of time that is taken on that chip. So the performance improvement has not been because of the faster computing power, it has been because of something else that's been happening around the computing power. And we'll see what that is there. But before going to that, let's see something which has been pulling the hairs of computer architects around the world. And this is what it is, the poor computer architect. The computer architecture is pulled around in one side by the standards, because it has to be compatible with all the devices that is there and that's coming out and that's been there earlier. And it has to support the videos, graphics that is being like some of this video, the one which you are looking at. It has to be error free, because if it is not error free, then Photoshop will not be Photoshop and this video might be displayed topsy-turvy. It has to be balanced, not because it has to have a central point of gravity. It has to be balanced and fair to all the applications and all the operating systems. Floating point is one another headache that is there, because it has to compute the value of pi, which is never ending. It has to cost less, or at least it has to be moderately priced. Otherwise it cannot be the cost of gold over here, or even the price of onions, as is the case. And then it has to be flexible, not that it has to be flexible physically, but flexible to do many tasks, multitask. And then graphics like the images, the audio, and then it has to be faster, and not exactly super fast, but at least it has to be faster, and real-time applications should be there. It has to be independent, not dependent on any other thing. It should be self-contained, it should be reliable, and energy coefficient should be such that power costs come down. So these are some of the aspects that any computer architect would be pulling his hairs out to solve. So what are the solutions for this? The computer architect, the ninja of computer architecture, has certain tools in his toolkit. It is the cache memory, that's the first tool in his toolkit, which can access the data for the CPU faster. And then there is the DRAM, which can help access the memory faster and memory improvements. The multiple instruction, multiple data streams, we'll see about those later in the future video series, which help him access and do tasks multiple times in the same time. And then overclock, it is like the medicine that the runners or the athletes take to have a burst of energy and get to do some things faster at a price. And then there is the die process, the die building process, which helps to keep the cost of the CPU and the computer architecture less. As usual, we have the Moore's law, wherein the transistors in the chip is there. Flash memory is for accessing the memory faster, it's like a flash. And then modularization, that which you saw in computer programming, is still applicable in computer architecture, so that there are certain different modules which can do certain tasks differently and execute it perfectly. Parallelism is like doing certain tasks in a parallel way. It's like the instruction line pipeline, which helps the computer to do things parallelly in a seemingly parallel manner. And then at the end there is a magnetic disk, which is more like the hard disk and the external hard drives, which help to keep the computer architecture in a different way. So with all these things, how do we go about and read it? How do we go about design it? For that, let's take an analogy of something which is intelligent and which is doing some work, and that is the human body. In the human body, we have certain things. The limbs are there, and then there is a head, which for most people we have brains, and then there is a heart, there is the nervous system, there is the blood circulatory system, and all those systems. So this is something which we know about the human body in a very basic thing of biology. Now, taking this as an example, like how the Wright brothers invented the aeroplanes by seeing of the birds, this is what is going to be the basis at which computer architecture is being there. So what we have here is a CPU, which is more analogous to the brain, and then memory unit is something like which is like our heart, and then bus is like the spinal cord and the nervous system. Parallelism is like the limbs that which can go about, and then IO devices are also like our hands and legs doing out the task. So with this as an analogy, we go about what the early computer architecture looked like. This is known as the von Neumann architecture. Looks pretty simple, isn't it? The CPU, the memory, the input and output devices all going through the bus, and there is a conductor who is going to do all this conducting task. The control bus, the address bus, and the data bus. We'll see about this von Neumann architecture later in the future video series, but then look at it in this way. This looks to be simple. There is a CPU, there is a memory, and then there is an IO, all controlled by a bus. Maybe it looks simple by the time it came out, but it is more like an evolution. This von Neumann architecture is like the ape over here sitting here, and then whatever we have, the computer architecture is mostly like this man or this man over here, the Neanderthal or the human. It's an evolution that has been there, but still the basic components of computer architecture has remained the same. What we see over here is a mobile processor. This is what is a current generation mobile mobile architecture, which is very similar in many ways to the von Neumann architecture that we have seen earlier. The antenna over here with the Bluetooth or the 802.11, the wireless, the GPS, the modem set, all constitute the IO devices. And then we have the bus, which is going to be the UART and the BT and all those buses that we have over here, which connects into it. The flash memory is going to be over here, shared memory, and we have the processors over here, the DSP processor and the ARM processor. The accelerators are more like the crow processors that we had in the over the day, and then the timers are like our pulses that is there in the human body, telling out yes, you have to beat 72 times per minute and all those. And then the SRAM, and then we have the display units, which is more like the IO devices or the limbs that are there. And then the keypad, the camera module, the battery is more like the life juice that's running through the man. So all in all, what we see here is a precursor, or the von Neumann architecture is a precursor to the modern day computer architecture. So this video series is just an introduction to what computer architecture is and what we can achieve and how we have evolved from the von Neumann architecture to the current architecture that is there in mobile units and the other set. Thank you for watching this video series. Join us in Facebook at facebook.com/Opengyan, or write to us at ping@opengyan.com. Visit us at opengyan.com. Thank you. Have a nice day. Meet you in the next video.